So we've got a question here. We need to solve z to the power of 6 minus 3iz cubed minus 2 equals 0. And we need to find the solution for z. Now, first of all, what we can see here is we've got this I here and the variable z. So we're into complex analysis. So z is our complex number, which is of the form of a plus bi, where I is our imaginary part. So that's the square root of -1. And a and b are real numbers with a real part and an imaginary part. Okay, now, next thing to look for in this here, we've got a polynomial of degree 6. So it's possible that we've got 6 solutions for our variable z. So order 6 gives us 6 solutions. There could be some that are the same value, but there will be up to 6 solutions. So that's the first thing we can sort of presume from the start of this question. Now on to actually solving it and finding our values for the variable z. Now, factoring this, I'm not too sure what to do at this stage, but what I have spotted is we've got z to the 6 and z cubed. So we can do a substitution for our z. So what we could do is have a new variable and have w and set that to z cubed. So if we do that, we'll then end up with w squared and w here, which will be in quadratic form, and then we'll be able to work with that a lot more easier than we will with this one of order 6. So let's go straight into the variable w. So z to the 6 is w squared, 3i is our coefficient for z cubed, which is w, and then -2, our constant, will stay and set to 0. Okay, so now we need to factor this out, or we could use the quadratic formula. Now, as we've got -3i here as the coefficient for w, and w squared with coefficient 1, we've got -2 here. Well, -2 plus -1 will give us -3. And if we do that in terms of I, we should have a -2i and an I for part of my factoring. So let's set this up. So we've got w and -2i and w and -i. Set that to 0. Now, -i times -2i, well, our real part will be +2, because -2 times -1 gives us +2. But I times I is I squared is -1. So we just make a note of that for there. So therefore then, I'm happy now with my factoring. I've got w -2i times w -i equals 0. So now solving that, I've got w -2i equals 0, or w -i equals 0. So therefore w will equal 2i or I. So that's what we've got there. So w equals 2i or I. So I'm just going to write it in that format. So that's what I've got so far. Okay, now all well and good, I've got w equals 2i or I, but I need z. Now z cubed, that equals w, which equals either 2i or I. So let's write both equations out and see where we can go from there. Okay. So now, for z on its own, I need to take the cube root of these two, and same here to get z on its own. So if we just put that there now, cube root of w equals cube root of 2i, and same for this one, cube root of w here, that equals cube root of I. Okay, now how are we going to find out what that is? Well, we need to use the de Moivre's formula, so we'll just write that out here now, and then we'll see if we can find the cube roots of these. So for that, we have e to the I theta n. I is our complex coefficient. theta is an angle, and n, that would be our power that we're raising our w to. Well, in this case, we've got cube root. So in here, our n will be 1/3. So let's set that up. And then we'll have a look at what our angle theta is. Now, before we do that, there's another way of writing this, which is r to the n. Now, r is a modulus of the complex number. So r equals the modulus of z, which will be the complex number inside these radicals. So we'll have the modulus of I and the modulus of 2i in these two cases. So that's something we're going to need to find. N we've already discussed, and then we multiply that by cosine of theta n, and that's all one input, and then add I sine of theta n for this one here as well. And that's the way we can write that out to find our cube roots. So now we need to find our angle theta. So now I'm going to draw I and 2i on the Argand diagram. So if I set that up over here, now I and 2i will be here. So that's my imaginary axis, that's my real axis, so that's my I, and this one here is 2i. So for the angle theta, we take it from the positive real axis, so this angle here is pi over 2. So that's what we have for theta. So let's write this down here. Theta equals pi over 2. Now there's rules for theta as well. So theta has to be in between minus pi and pi. Now it can equal pi, so it has to be less than or equal to pi, but also greater than minus pi, but strictly greater than pi. That's what my angle theta has to be in a range. So as with in complex numbers there is infinite solutions, I could also write this angle here as increasing by 2 pi, which would give me 5 pi over 2. 5 pi over 2 is not in this range, but pi over 2 is. So therefore that's what's called our principal value for our angle theta. So theta equals pi over 2. Okay, so that's all good information so far. So now let's go into our solutions here for this equation. Let's take this bit off the board. Now we've worked that out, and now we can write e to the I theta times n. So pi over 2 times n is pi over 6. So then that equals r to the power of n. Well, r is I. Now the modulus of I, let's just work that out. So the modulus of I, that's just 1. And the modulus of 2i, that will give me 2. So that's my corresponding modulus for both values. Okay, let's take this off the board. So now let's work out for this one here. That's going to be the easiest one to take care of first. So let's just put a box around that one. That's what we're interested in. So e to the I pi over 6 equals 1 to the power of a third. So it's going to be 1 to the power of a third. So that's just 1. So I'm going to put that in anyway. And then cosine of theta times n, which we have here, which is pi over 6, plus I sine pi over 6 as well. Obviously both angles are equal. Okay, so now we're to simplify this off. Cosine of pi over 6, we know that is root 3 over 2. And sine of pi over 6 we know is a half. So it's plus I over 2. And 1 to the power of a third is just 1. So therefore that is one solution for z. So I could call that z1. Okay, now when we're taking the cube root, there is 3 solutions. So again, back to our Argand diagram. If we've got pi over 6, which is this angle here, remembering these parameters here for our range of pi, if there's 3 solutions, they will be equally spaced out from pi over 6 in different values, in different distances from each. So from pi over 6 with 3 different values, there we could add 4 pi over 6 and subtract 4 pi over 6. So then that would give us our values that we want. So let's do that. So add 4 pi over 6 to pi over 6 gives us 5 pi over 6. So that would take care of that one. And the other value, pi over 6 minus 4 pi over 6 is minus 3 pi over 6, which is minus pi over 2. So that's where the other values are. Okay, so now we're going to keep this value here and then continue with this and calculate our other values for our other cube roots. Okay, let's take this off the board and do. Okay, so now I've got z1 is root 3 plus I over 2. I've got that for pi over 6. Now let's have a look at 5 pi over 6. So that can be my second value when we've got modulus 1 for I. Now 5 pi over 6 is reflected in the real axis. So with that, we know that cosine is negative in this quadrant, positive in this quadrant. So as cosine is the real value of our solution, we can just now write minus root 3 and go straight into our z2 value because the imaginary component will stay the same. So that's a shortcut way there we can write for our second solution. And now we need to find our third solution, which is pi over 2. So for the third solution, I've got my real part will be 0 because cosine of minus pi over 2 is 0. And then sine of minus pi over 2 is minus 1. Multiply that by I get minus I. So z3 is just minus I. Okay, so that takes care of my 3 solutions for I. So these are all the values for I. Now let's have a look at 2i. Well, for 2i, my values along the quadrant in terms of its argument are going to be the same, but my r to the n is going to be different. So let's just take this pi over 6 for the first one. My modulus of 2i, that equals 2. So then I've got 2 to the power of n, which is 2 to the power of 1/3. And then cosine theta n, well here I've got pi over 6 because that's going to be pi over 2 times 1/3, pi over 6, plus I sine of pi over 6. So that's going to give us the same result as this, but with a multiple of cube root of 2. So then that equals cube root of 2 multiplied by this value here, square root of 3 plus I over 2. Now that will be my z4, so that's my first one for 2i. My z5 will be the same with this one, with the multiple of cube root of 2. So z5 will be cube root of 2 minus root 3 plus I all over 2. And then my sixth one will be the same as this with this multiple. So z6 will be the cube root of 2 times minus I. So that's going to give me all 6 of my solutions to this polynomial here. So my first 3 are here when dealing with 2i, and when dealing with I, I've then got these 3 solutions. Okay, and then that is my solutions taken care of for this polynomial. Okay.